Hi everyone, my name is Yurii. I have been building business systems for 20 years, and I'm honored to present a topic that is dear to my heart here today, even if not in person. I've had a great time meeting the community in Shanghai earlier this year, and I'm looking forward to meeting many of you in the near future. The topic of my presentation can come off hyperbolic, I get that, but here's the thing. I want to talk about today's problems that are stemming from the past and the vision of how we can keep moving towards the future while grounded in reality. Something we can have in production, not in 5 years. A few years ago, I founded Omnigress to bring this into reality. Let me be completely honest with you about the challenge of this presentation. I struggled to prepare it until the very last moment, working on something that questions how we have been doing things for the past decade, challenges the established status quo. I constantly find myself in this weird spot. There's too much to tell. Every thread I pull connects to 3 more problems, and before I know it, I'm inching into covering half of the stack. But there's also too little to tell that fits into our existing mental models. So please, bear with me. I've got to start somewhere, so I'll start at the end game to set the expectations, even if it sounds a little outrageous. Tomorrow, there will be no databases. And I get it, we are at a database conference, but hey, if we were sharing today's software architectures with people in 1995, they'd look confused too. When someone tells you that fundamental building blocks of our industry are going to disappear, it's natural to feel unsettled. But we have been here before. Let me explain what I mean. There won't be a database as this separate thing that lives over there that you connect to over the network and issue queries and commands at. However, I'm not talking about eliminating databases. I'm talking about evolving them into something much more powerful. It's about recognizing that data is not just about storage and retrieval. It's the living foundation of every business system we build. Here's something that's been bothering me lately, and it gets to the heart of why I think we need this architectural shift. I keep hearing this question at conferences and in conversations with leadership. When can I fire my developers? It illuminates the distinction between excitement about AI helping code and the excitement about running a faster, leaner ship. Now, I understand the economic pressures, but this question reveals a fundamental misunderstanding of what our real problem is. It assumes developers are the bottleneck. The human creativity and problem solving are the expensive parts we need to optimize away, and let AI be the agent of that. But that's not the real problem. The real problem is that we're forcing brilliant developers to spend their time on busy work, on building and maintaining complex architectures that exist primarily to work around the limitations of our current tools and paradigms. When a senior engineer spends 3 days debugging distributed tracing across microservices, that's not valuable work. When a team spends a sprint implementing retry logic and circuit breakers for service-to-service communication, that's waste. When architects spend weeks designing event sourcing patterns to maintain consistency across service boundaries, that is solving problems we have created for ourselves. Simply moving this to a fast pattern matching engineer running on myriads of GPUs creates more code, more liability. Why does this matter? Because it shows we're solving the wrong problem. Instead of asking, how do we need fewer developers? We should ask, how do we focus on business value instead of accidental complexity? And the problem isn't developers, it's over-engineering. And I say this as someone who has been guilty of it myself. Our industry has become obsessed with complexity for its own sake. We have convinced ourselves that good architecture means distributed architecture, that scalability requires microservices, and that the modern applications must be composed of dozens of independently deployable services communicating through message queues and API gateways. But here's the thing, and I learned this the hard way through multiple startups and consulting engagements. Most applications don't need this complexity. Most businesses do not operate at the scale where these patterns provide a significant benefit. Yet we have made them the default, the standard approach that every team is expected to adopt, regardless of their actual requirements. There's a time and place for them. But I've seen teams of 5 developers managing 12 microservices, each with its own database, its own deployment pipeline, its own monitoring stack. And I've seen simple CRUD applications split across multiple services because that's how you do microservices. I've seen companies spend more time building and maintaining their service mesh than building features that customers actually want. The goal should be to need less bespoke code in the first place. Less boilerplate, less infrastructure code, less glue logic that every development team has to write and maintain. Less time spent on problems that shouldn't exist. Here's something I believe we may have lost sight of in our rush toward distributed architecture. Data is the core of business systems. Not applications, not services, not APIs or message queues or container orchestration platforms. Data. Your customer records, your transaction history, your inventory levels, your user preferences, your audit trails, your business rules, your workflows. This is what your business actually is. Everything else is just machinery for creating, reading, updating, transforming, and deriving insights from that data. Yet our current architectures treat data as a second-class citizen. We design our applications first, then figure out where to stuff the data. We optimize for service boundaries and deployment independence, not for data consistency and query efficiency. We accept data duplication because our service communication patterns require it. We tolerate eventual consistency because our distributed architecture demands it. This leads to a fundamental inversion that I think is at the root of many of our problems. Instead of applications serving data needs, we force data to serve application architecture decisions. We scatter related information across multiple services because our microservice boundaries require it. We duplicate data across systems because our service communication patterns require it. We accept eventual consistency because our distributed architecture requires it. But what if we flip this around? What if we started with the principle that the database serves the business and not the application? What if we began with optimal data modeling and built everything else around efficient data operations? Let me paint a picture of where we are today with contemporary data architecture, because I think it's important to understand exactly what we're working with before we talk about alternatives. The current blessed approach is designed for scalability, flexibility, and modularity, and these are genuinely valuable goals. I don't want to dismiss the real benefits that distributed architectures have provided, but the way we achieve these goals creates new categories of problems that often exceed the problems we were trying to solve. We prioritize decoupling above all else. Applications and databases are designed as separate entities, enabling independent scaling and modular development. This sounds great in theory, but in practice it means that every interaction between business logic and data requires network calls, serialization, deserialization, connection management, and complex error handling. With data distributed across multiple systems, movement and synchronization become key operational concerns. We spend enormous effort building ETL pipelines, maintaining data lakes, implementing event streaming platforms, like Kafka, and ensuring consistency across replicated datasets. Companies hire entire teams just to move data around. We embrace shared nothing architectures, where messaging systems and event-driven patterns help services communicate and maintain eventual consistency. But eventual consistency can be an euphemism for sometimes wrong. And the complexity of debugging distributed state machines often exceeds the complexity of the business problems that they're supposed to solve. Finally, we rely heavily on external services, specialized third-party services like authentication, payments, logging, analytics, monitoring, alerting. Each integration point becomes a potential failure mode, a vendor lock-in risk, a source of operational complexity, and another thing that can break at 3 a.m. So what are the practical day-to-day problems with this architecture? I want to be specific here because these aren't theoretical concerns. These are problems I've debugged at 2 a.m. First, latency and performance. Every round trip between services and the database introduces latency, potential failures, and stale data. The more steps involved, the more data being moved, the worse it gets. What should be a simple business operation, like calculating the customer's account balance, becomes a distributed transaction involving multiple services, each with its own database, its own failure mode, its own performance characteristics. Second, cognitive complexity. When logic is scattered across services and databases, knowledge silos form. Understanding how a simple user action flows through the system requires deep knowledge of multiple code bases, data models, communication patterns, and failure scenarios. Debugging becomes painful because you're not debugging a system, you're now debugging an ecosystem. Third, operational overhead and hidden costs. Service-oriented architectures require extensive observability and monitoring just to understand what's happening. They often lead to race conditions, complex rollback logic, and inconsistent data states that are difficult to detect and even more difficult to resolve. The operational complexity of running dozens of services often exceeds the operational complexity of the business itself. Finally, team velocity impact. Microservices were designed to help teams move faster without stepping on each other's toes, but in practice, the overhead of coordinating across fragmented services often slows everything down. Simple changes require coordination across multiple teams, multiple repositories, multiple deployment pipelines, and multiple operational concerns. Now, let me introduce what I call data-native architecture, the alternative I've been building at the foundation of OmniGres, where contemporary architecture optimizes for scalability and flexibility. Data-native architecture optimizes for efficiency and simplicity while maintaining the ability to scale when scaling is actually needed, not before. The core principle is data first. We build from the data layer up, ensuring consistency across interfaces, operations, and security. Comprehensive data modeling forms the foundation for seamless architecture. Instead of retrofitting data stores to application designs, we start with the optimal data representation and build application logic that works directly with that representation. This enables what I call contextual runtime placement. Code executes where it's most efficient, inside the database when performance and locality matter and resources are, in fact, available. When compute needs exceed what's available in the database, the compute can be scaled out without changing the code. The database remains the system's center of gravity, but it's a much more capable database. Crucially, this doesn't mean going back to the bad old days of stored procedure development with cryptic PL/SQL procedures and no version control. A system like this should provide expected development workflows, leveraging Git, text editors, CLI tooling that give you the performance and consistency benefits of executing logic close to the data with the development experience you expect from modern tooling. And importantly, it's not an all or nothing approach. Data native architecture supports gradual adoption and integrates seamlessly with external services or, say, Kubernetes environments and hybrid cloud deployments. You can start with critical business logic and gradually move more functionality into the data native layer as you see benefits and build confidence. I want to address something directly. Integrated data processing isn't a new idea. I'm not claiming to have invented something revolutionary. I'm building on decades of experience and learning from both the successes and failures of previous approaches. And that's a great thing. In the 1960s through 1980s, early integrated database systems like MUMPs, which evolved into systems like Cache and GTM, pioneered embedding logic within the database to optimize performance. These systems powered healthcare, banking, and real-time transaction processing, and many still do today. They proved that integrated architectures could deliver exceptional performance and reliability for mission-critical applications. In the 1990s and 2000s, enterprise databases from Oracle, Informix, and Sybase all embedded procedural logic inside the databases to enable transactional efficiency. Stored procedures, triggers, and PL/SQL-like languages became the standard for tightly coupled business logic. These systems powered the world's largest enterprises and most critical financial applications. But then in the 2000s through 2020s, as microservices and big data systems evolved, data fragmentation increased, leading to higher complexity. The pendulum swung hard toward distributed architectures, and we largely abandoned integrated approaches in favor of service-oriented ones. This wasn't necessarily wrong. The hardware constraints and operational practices of the time made distributed approaches more practical. However, we're now seeing reintegration. Snowflake's Data Cloud, BigQuery's user-defined functions, and various edge computing platforms all show a return to processing data where it lives. The industry is recognizing that the cost of data movement often exceeds the benefits of service independence. So why is now the right time for this architectural shift? Why didn't we just stick with the integrated approaches that worked in the past? Well, first, hardware capabilities have fundamentally changed. High-performance NVMe storage, fast multi-core CPUs, and abundant RAM removed the old constraints that made integrated architectures impractical. The performance characteristics that once forced us to separate compute and storage no longer apply. Modern database servers can run complex application logic at speeds that were unimaginable when we first started building service-oriented architectures. And scaling compute with data is now feasible, making deeply integrated processing more viable than ever. A single modern server can handle workloads that required entire clusters just a few years ago. Memory is cheap, and it's cheap enough that we can keep entire working datasets in RAM. Storage is fast enough that complex queries don't create bottlenecks. Second, the data-related demands have intensified dramatically. AI, automation, and real-time analytics require structured, immediately available data. Businesses can't afford slow, fragmented architectures when they're trying to compete on data-driven insight and real-time responsiveness. The latency and consistency requirements of modern applications often exceed what distributed architectures can reliably deliver. When you're trying to provide real-time personalization or fraud detection or operational intelligence, the overhead of distributed data access becomes a critical bottleneck. When every millisecond matters, data locality becomes paramount. So how do we actually get there? The path forward involves three main areas of development, and I would want to be specific about what each entails. We need to make it practical and reliable to run complex application logic within database environments. This means better resource management so that analytical queries don't interfere with transactional workloads. It means process isolation so that one function can't crash the entire system. It means comprehensive monitoring and debugging tools so that developers can understand what's happening inside the database. It means operational workflows that are familiar to application developers. The most transformative improvements will come from outside the core, where developers are free to experiment without the constraints of backward compatibility or committee consensus. Developers should be able to extend the system without asking permission, much like how web development flourished through open standards and client-side innovation. And we need a platform that encourages the boundary-pushing work and provides clear pathways for these innovations to eventually migrate into the core. This brings us to a crucial question: why build this on Postgres instead of starting from scratch or using another database system? There are three fundamental reasons why Postgres is the right foundation for data-native architecture. And I've thought about this extensively because choosing the wrong foundation could doom the entire project. First, it's advanced and extensible. Postgres has advanced capabilities and features that most people don't even know about, with long-term extensibility goals built into its core design. Unlike many database systems that are essentially closed platforms, where you can only work with predefined boundaries, Postgres was designed from the ground up to be extended and customized. The extension system allows you to add new data types, new functions, new operators, new storage engines, and so on. Second, it has trust and maturity. Postgres is reliable software that has developed over multiple decades and deployed widely across industries and use cases. It has proven itself in the most demanding production environments: financial services, healthcare, government, e-commerce. When you're building something that will handle business-critical data, you need a foundation that has been battle-tested. Third, it has community and growth momentum. Postgres is the most popular open-source database and is becoming a universal data platform. The ecosystem, tooling, and expertise around Postgres continue to grow rapidly. There are more Postgres developers, more Postgres tools, more Postgres hosting options than ever before. Building on Postgres means building on a foundation that will continue to grow and evolve. Let me give you some concrete examples of what's possible today and what's coming tomorrow, because I think it's important to ground this discussion in real capabilities. Today, Postgres already supports polyglot functions. You can write functions in multiple programming languages, including Python, JavaScript, and many other languages. It supports background workers that can run continuous processes within the database, job queues, data replication, maintenance tasks, or even completely novel uses, like supporting new network protocols. It has custom table and index storage capabilities that allow you to optimize data layout for specific use cases. It supports custom indexes that can dramatically improve query performance. And importantly, it has hooks throughout the system that allow extensions to modify core behavior. Tomorrow, we might have multi-threaded query execution that will dramatically improve performance and capacity, where we might get new executor models that optimize for different workload patterns: OLTP, OLAP, streaming. There are experiments with syntax extensions that will make it easier to express complex business logic directly in SQL or new augmented syntaxes. And who knows, maybe one day we will be working toward using the Postgres core as a library, allowing to be embedded in applications while maintaining. But here's what really is exciting. These aren't minor improvements. They are fundamental expansions of what a database can be. They turn the database from a passive storage system into an active computing platform. Postgres is community-driven, and while open collaboration can be a blessing, it can also be a curse, resulting in multi-pronged focus areas that don't always align with commercial needs or timelines. And the community prioritizes stability and backwards compatibility above all else, which is generally good, but can slow innovation. There is a significant change friction it is getting more difficult to radically augment and improve Postgres, both for technological and social reasons. The code base is mature and complex, with decades of accumulated assumptions and optimizations. The community is rightfully conservative about changes that could affect stability, performance, or compatibility. Getting significant changes accepted into core Postgres can take years. Finally, there are architectural limitations. It's difficult to predict the future and evolve over decades. The core architecture has some limiting assumptions and designs that were made decades ago when hardware, use cases, and operational practices were very different. Some of these limitations can be worked around with extensions, but others require more fundamental changes. Many developers and operations alike fear the database. They really are trying to box it away and build a perimeter around it, and I don't blame them. Databases could be intimidating to learn, use, and operate. But the problem with this is that it leads to cautious, shallow use, sticking to a very limited subset of database functionality, bordering with dumb storage territory, and it really pulls people away from understanding and realizing the full power of databases. Understanding this gives us an opportunity to help these users grow. Here's a good example I'm very passionate about. I've built BPMN and Amazon Stays Languages workflow engines before, and I keep seeing advancements in this space in the databases, which is particularly exciting. But I've noticed one thing. The workflows tend to be defined as code, either in its textual form or as a diagram, and the database is used to store the state, effectively the pointer to the next step. However, having instances of these workflows represented through this gives us no business language to ask the database about user's journey, how they affect the business. We query the program, not the domain. And it gets worse because we don't live in a static world. Workflows change. And if a user was going through one, what should happen if a workflow gets updated? The biggest insight I had is that workflows are not sources of truth. They are emergent properties of state transition. And this leads us to a simple idea. We should, as intended, capture the state of the world, record assertions of truth in the language of the domain model, and allow for the transitions to happen according to the business rules. This enables us to query the world about the actual business state, not the program state. And there is no versioning and upgrades of workflows because they don't explicitly exist, but can only be captured as an effect. So all of this brings us to Omnigress, my answer to these challenges and the concrete implementation of the data native architecture I've been describing. Omnigress is an open source stack built on a reliable and trusted foundation of Postgres, the most trusted open source database. We turn it into a complete data native platform through several key innovations that address the practical problems I've encountered building real systems. We're making Postgres a complete system requiring no external tooling for most common application development tasks. No separate application servers, no separate job queues, no separate API gateways. Everything runs inside Postgres with the performance and consistency benefits that it provides. We're bridging long-standing development and deployment gaps that have made database-centric development cumbersome. Modern version control, automated testing, continuous deployment, all the practices that application developers take for granted, now available for database-centric development. We're enabling teams to build business logic in Postgres in multiple languages with modern development workflows. You can write functions in Python, JavaScript, Rust, or simply PL/SQL, and deploy them with the same tools and processes you use for application code. We're adding API server capabilities to Postgres so it can serve HTTP requests, WebSocket connections, and other network protocols directly. No need for a separate web server or API gateway. Your database can be your complete application platform. And we are developing business components like OmniLedger that provide built-in solutions for common business requirements. Instead of building an accounting system from scratch, you can use a proven ACID-compliant ledger that's built directly into the database. Crucially, all of our software operates on unmodified vanilla Postgres. We're not forking the database or creating vendor lock-in. Everything we build enhances standard Postgres installations and can be removed if you decide to go a different direction. Our development efforts fall into three main categories, each addressing different aspects of the data native vision. First, foundational work. We're improving cluster operations to make it easier to deploy and manage Postgres at scale. We are enhancing schema management to support modern development workflows with version control and automated migrations. And we are working on query plan augmentation to optimize performance for data native workloads, where business logic and data access are more tightly coupled. Second, new capabilities. We're adding networking support for HTTP APIs and WebSocket connections so applications can communicate directly with the database over web protocols. We are building an extended extensions API that makes it easier to add custom functionality. And we're developing advanced types and reactive queries that enable real-time event-driven applications where data changes automatically trigger business logic. Third, business components. We are starting with OmniLedger, a complete ACID-compliant accounting system built directly into the database. This gives applications immediate access to financial primitives like accounts, transactions, balances, and financial reporting without requiring external services or complex integration. You can implement double entry bookkeeping, multi-currency support, balanced books, and financial controls with simple SQL operations. Traditionally, if you wanted to extend Postgres, you had to write C code, which limited extensibility to a small number of expert developers who were comfortable with memory management, pointer arithmetic, and the intricacies of Postgres internals. One of the most prominent projects in this space is PGRX, which enables the use of Rust to develop extensions to avoid these issues. I contributed to this project before. However, Rust is a completely different language requiring its own toolchain. So we have eventually invested time into developing CPPGres, a header-only C++ library that simplifies development of Postgres extensions without requiring to completely abandon the family of the languages and the toolchain. One of the immediate benefits of this development was that we were able to leverage transparent offset pointer translation for near effortless shared memory use, which is traditionally quite painful with existing primitives in Postgres. And the goal behind CPPGres is not just to have the library, but rather also to become a structured API of Postgres functionality intended for discovery and learning. Much of the difficulty in developing Postgres extensions comes from a vast namespace and the multitude of conventions and gotchas that one has to learn. And our stretch goal goes beyond a one-to-one mapping. We want to provide additional primitives that make things that are difficult today accessible, like MVCC-aware containers that can provide transactional guarantees for complex data structures. These kinds of innovations are only possible when you have deep integration with the database engine, and they open up entirely new categories of applications that simply aren't possible with traditional architectures. Finally, it's now becoming my little ritual to leave the audience with a few questions to ponder. I would love to hear back from you if you have any thoughts. First one, what builds trust in a database? What makes us feel safe to use one? What if columns had no names? This might sound absurd at first, but think about it. Column names are really just human-readable labels for positional data. What if we could reference data by semantic, ontological meaning, or structural relationships rather than arbitrary names? And number 3, can schema migration be treated as a database migration? Currently, we think of schema changes and data migration as separate processes. You change the structure, then migrate the data, but what if we had no DDL to change the tables? It can only create new ones. Think about it. And that's all. Thank you for your attention and for being open to exploring these ideas with me today. I know I've covered a lot of ground, from analyzing our current architectures to proposing fundamental changes to how we think about data and computation. I know some of these ideas challenge conventional wisdom and may seem impractical or even impossible given our current constraints and the momentum of the industry. But I believe we are at an inflection point. The same forces that drove us toward distributed architectures, the need for scale, reliability, and developer productivity, are now pointing us toward integrated data-native solutions. The hardware capabilities exist, the demand is clear, and the foundational technologies are mature enough to support this evolution. Omnigress represents an attempt to bridge the gap between where we are and where we need to be. We're not trying to replace everything overnight or force everyone to rewrite their applications. Instead, we're trying to provide a path forward that builds on proven technologies while enabling new possibilities for those who are ready to explore them. I encourage you to explore our work, try our tools, and contribute to our open source projects. And most importantly, question your own assumptions about what's possible with data architecture. The future of application development may look very different from where we're building today. And I believe it will be simpler, more powerful, and more aligned with how businesses actually work. The conversation about tomorrow's database starts today, and I hope you'll be part of shaping what comes next. Thank you. 谢谢。